Okay, so we're going to look now at the homework that we have assigned or the application problems that we have assigned for Module 2. Now, as I stated earlier, we're going to look at our application problems. We're going to click on the top document here, okay? And then you're going to notice that we have 9 problems that we're going to do. So what I want to do is just go into the chapter, find each one of these, just make sure you have a good understanding of what we're looking at. And that if you do have any questions, I'm happy to answer those along the way. So let's start by going to page 26 and looking at problem 2.1. Okay, so I'm going to pull this underneath here. Okay, problem 2.1 is the first problem here. Now, as you recall, we had said we are going to be doing 2.1 analytically. It says, the problem statement says, determine graphically the magnitude and direction. I want you to draw a sketch how you would graphically do that, but then you're going to solve for the numbers using the sine or the cosine law. All right, and or, okay? So you're going to look at this problem right here. You've got 900 newtons and 600 newtons. You're going to draw this in a tip to tail method, and you can probably use the triangle method or the parallelogram method then to show how you would solve that graphically, just as a diagram. But then using that diagram, you're then going to determine the magnitude of the resultant and its angle, okay? This was like the first 2 or 3 problems that we did in the sample problems, okay? All right, so that's your first one. Your next one is 2.5, okay? Here we have a steel tank. It's positioned, as you can see, knowing that alpha is 20 degrees on this side, determined by trigonometry. That's going to be the sine cosine law, all right? The required magnitude of P and what the resultant would be, okay? Now, the resultant, it says here, is vertical. So if we look at this problem, and I'm gonna draw an illustration here. And this is problem 2.5. Okay, just as an overview. I'm not going to work the whole thing. I just want to show you the diagram. Okay, so I'm going to draw an X and a Y. Okay. That intersection is going to be point A. All right. Now, we know that we have 425 going at a 30-degree angle. So I'm going to draw that. I know both its magnitude and direction. So I know this to be 425 pounds, and this is a 30-degree angle, okay? I also know that my resultant is going to be along this line, okay? I don't know exactly where it ends, but it's going to be vertical, as it says in the problem statement, okay? We know that P is going at angle alpha, which says in the problem that it's 20 degrees. So it would be 20 degrees. I'm going to draw this lightly to the horizontal over here, okay? Physically. But we're going to draw this tip to tail with that 425. So because we want to find the resultant. So if I take and I put another horizontal line through here, just as a reference, okay? My P is going to be 20 degrees off of this. You kind of see what's happening here? So now the tail of P is going to be at the tip of the 425. And then where it intersects with the vertical is going to be where my resultant ends. Does that make sense to everybody? Okay. So you've got 425 plus P is equal to the resultant. The resultant tip is going to be at the intersection of where P is. We still don't know what our resultant P is, or resultant is, and what P is, but we know some things here. We know that this is 425 and this is at a 30-degree angle. This is a total of 90, so that means that this one is 60 degrees, right? We have another 90-degree triangle here, and by geometry, this is 30 degrees there, right? Now, from horizontal, we knew that P was going at a 20-degree angle, right? So do you see how this is 50? Side opposite of that is going to be your resultant, okay? And if we look at this angle right here, okay, if this is 20, Here's another right triangle. This is 70. We know that 425 is opposite the 70. So you could use the sine law, right, to get your resultant, and then probably the sine law again to get your P, right? So this is kind of the key here, is kind of setting it up so that you can see how that works, okay? Because when they're on both sides, it's like, ooh, what am I going to do with that? Use the tip to tail resultant method. Yes.
Like on Monday, you said I could use the
Rectangular component method. That's
Is
okay.
that okay for this one?
Yeah.
Okay,
Mhm.
as long as okay.
Yeah, you guys now know, if you would, 3 ways of solving these problems. You know, graphical, all right? That's how we're going to sketch it out. You know the sine, cosine laws, right? And then you now know the rectangular components. So you can use any one of those 3. This happens to be in the section where they were doing the sine and the cosine laws to solve them. So that's kind of like where I headed with them. But there's multiples now, the way that you can solve this. Any other questions on this one? Okay, so just kind of wanted to give you an insight on how to solve for that one. Okay, and then I think the next one that you have is 2.7. I'm just going to confirm that with here. Yep, 2.7. So 2.7 is going to be found on page 27. We have a trolley that moves along a horizontal beam. It's acted upon by 2 forces. We see them right here through point A. Knowing that alpha is 25 degrees determined by trigonometry, sine, cosine law. You could use the rectangular component method if you wanted to at this point as well, to find the magnitude of force P. So how long is that? Okay. So that the resultant force is exerted on the trolley car vertically. So the resultant is going to be pointing down along that vertical line. So similar really to the very last problem that we looked at, okay? And then what is the corresponding magnitude also of the resultant? So you're trying to find P and the resultant that goes down, all right? So you can use that very same approach of tip to tail with these 2 vectors, and then where it intersects with that vertical, but this time it's going down instead of up like we saw in the last one. Does anybody want to see that setup, or you feel comfortable with that? You'd like to see it? Okay, then let's look at it. So this is going to be 2.7. Okay, so problem 2.7. Okay. And this one, because our forces are going to be going down, okay, I'm going to draw my horizontal this way and my vertical going straight down, okay? So this would be, if you would, the negative y, and this would be our x. Now, I always like to start with whatever we know the most about. So we know on the left-hand side here that we have 100 newtons going down, 1600 newtons going down and to the left. So this is 1600 newtons, and this is a 15-degree angle. Okay. Now, in this problem, it said, bless you, from vertical, this alpha angle in the problem says it's 25 degrees, okay? So that means I'm going to go like this. Okay, I'm going to draw this in here, vertical, all right? And this is tipped 25. I'm gonna exaggerate it because I need to intersect with my vertical. So I'm gonna exaggerate that angle. Okay, but it's 25 degrees. So I want it to intersect here. Okay, so on the end point then, there, this is gonna be my P. And this is gonna be 25 degrees right here. Okay. So now my P, because this is my vertical, remember from here going down is going to be my resultant. My resultant needs to be going down, and it is going to point at the intersection right there. So that's going to be my resultant. And then P, its tail is going to start at the end of the 1600 newtons, and its tip is going to go to that intersection. Okay. So now, angles. Okay. I'm going to put through here 90-degree angle, okay, just so that you can see that it's 90 degrees to here as well. So now if I know that this is 15, do you see how this angle is 15 degrees, right? And if I know this is 90 degrees and this is 25, how much is left over here? Is it 65? 65 plus 25 is 90, right? Okay. So that means the total angle here is going to be 80 degrees, right? If this one is 65, this one is 25, this one is 15, this one is 75. There we go. So now you have all the internal angles, right? You know, one of the sides, so you should be able to solve for the magnitude of the resultant and the P here, right? Like it's asking for. Again, I would probably start with the sine law, right? And do those. You can do that. And again, if you are like, I really like the rectangular component method, you can go that way too. Okay, because you do have that knowledge now. But then you would be setting this up differently. All right, any questions on that? Okay, that's 2.7. So those are the three problems from our first section, okay? So then we're gonna go to the next section. I do have some of these. All right, so we're gonna do 18, 19, 22, 26, 27, and 31. Yep, they're all in this next section. Okay, great. So going back underneath, let's look at problems 218 and 219. They're on the bottom of page 35. So on the left-hand side here, it says, determine the X and Y components of each one of the forces. So you're not finding the resultant for this, but there are three forces on number 18, and there are three forces on number 19. You need to find the X and Y components for the 60-pound force, the 40-pound force, and the 50-pound force for 18. Okay. Now, somebody asked me earlier, can I put these all in the same diagram? You certainly could, but make sure that the diagram is large enough so that you can show and label each one appropriately. Don't make them small. If you're making them smaller, then probably one diagram for the 60-pound, one diagram for the 40, and one diagram for the 50. Does that make sense to everybody? Okay. Does anybody want to see what I mean about that? And then it's the same thing for number 19. So this is just components. You're not finding the resultant here. You're finding, you know, three individual components, two components each, so 6 total for each one of the problems. So it's practice components. The important things here are label the forces. So in this case, it's just calling it 60 pounds. I would call that F1, F2, F3, or A, B, C, okay? And then correspondingly, you would have an AX, an AY, or an F1X, an F1Y. You would have those labeled. And then when you're solving for those in the work, then wherever you solve for them, I should be seeing that labeled appropriately on the diagram. Okay, just like we did in the problem. So any questions on that? Okay, so that's 18 and 19, just components. Okay. Then as we turn this one over, number 22. 22, and its illustration is right here on the left-hand side. It says cable AC. So starting down here, okay, cable AC up to there. On beam AB has a force P along here, along AC. So force P is along the actual cable itself. Determine, or knowing that P must be 350 pounds. Oh, in the vertical component, I didn't read that right. 350 in the Y component here. Determine the magnitude of P and the horizontal component. So for this one, I'll kind of draw this one out for you as well, because there's a lot going on there. So if we look at where point A is, all right, point A is out here. Okay. Point B is over here. And then directly above B is point C, okay? And A connects to C with a cable, okay? Now, they're telling us in our problem that this is 55 degrees right there. This would be a 90-degree angle, okay? And that along this cable, okay, the force in that cable going up and to the right, they're calling force P, okay? The 350, as identified in the problem, we're going to draw a Y component going through A. We're going to go straight over to that vertical line, okay? The Y component here, the vertical component of P, PY, is equal to 350 pounds, okay? You want to find P, and you want to find the X component, which would be right there. Okay. Now, we know that this angle right here is 55 degrees. We know that this is 90 degrees. What would this angle be? 55 plus what gives us 90 degrees? 35, right? 35 plus 55 is 90, plus 90, I've got 180 inside, right? So now knowing that angle, you can find the X component. And remember, our Y is equivalent over here, but the Y is going to be at point A, okay, in the vertical direction. So any questions on this one? Feel like you can kind of take it further and find the resultant, if you would, P and PX. Okay. All right, so that's 22. 23, I'm sorry, 26. Goodness. 26 is our next problem. It says determine the resultant of the three forces in 218. Okay. So now you are going to determine, we go back to the previous page, what is the one force that would replace all three of those? Okay. Like I would do, there are three forces that share that same point, concurrent force system. I would do the rectangular component method for 226. So for 226, I would do rectangular component method for problem 218. Now, the nice thing is when you did 218, or when you would have done 218, or you're gonna do 218, you'll have the components already figured out, okay? So this might be a case for, that I might put them all on the same axis system because I'm going to be using that for 26 anyway, right? So we're going to use that process where you find the components. You're going to add and subtract in the X and Y directions to get those resultant X and Y components. And then you're going to use those to find the final resultant.
So, so for 226, for the diagram, do we only have to have the resultant, or do we have to have all of them?
All of it. Yeah. So you're going to mimic what we did for sample problem 2.7. You're going to start like this. Okay. You're going to do your components. You're then going to sum your forces in the X and Y to get the resultant X and Y. And then you're going to do the final diagram showing the X and Y resultant components, solving for that. So that would be the full rectangular coordinate or rectangular component method. All right, so that would be number 26. So following that very same process we did for sample 2.7. Okay. And then the same thing for number 27. Number 27 at the top of the next page says, determine the resultant of the three forces for problem 219. Problem 219, you calculated the individual components. So again, rectangular component method to solve for the final resultant. So again, starting with your diagram, right? Doing the components, which you will have already calculated based on 219. then summing your forces in the X and Y direction, and then doing the final resultant. Okay. And then you have one more problem to do. All right. So any questions on 26 and 27, doing the full rectangular component method? All right. So then the last problem that you have in this section and the last problem you have for the assignment is number 231. Says for the post loaded as shown. Okay, so here's the post from C to B, and at the center of C, we've got two forces acting. Okay, we want to determine the required tension in rope AC if the resultant of the three forces exerted at C is to be horizontal. And then what is the corresponding magnitude and the resultant of those two forces? Okay. So that one, again, rectangular component method. All right. But what is the tension in AC? So here is this one. You're going to draw another force along here. Okay. Now, in this case, they're not giving you angles, but they're giving you the slope of the line so you can calculate the angles. All right. So, so notice here that they're giving you the slope of each one and they're giving you the height and the one on the left. So you're going to just find the resultant of the three that you have here. And it says that the resultant is going to be horizontal, right? Yeah. Going through point C. So your resultant force is going to be somewhere along there. Okay. So that one will probably be the one that you have to put a little bit of thought in, but I want you to think about that one for a little bit. And then you can always ask me questions, you know, as you've kind of looked at it and seeing what you can do with it. Now we are at the point where I am going to stop our recording